Okay. Now I will take my pleasure to introduce the second speaker. But anyway, before starting my introduction to the second speaker, I will say something about my experiments in 94, 95. I took my pleasure to participate almost 20 years ago, maybe,
yes.
in UC Berkeley. It was a human game tournament.
Yes.
Hex tournament.
Yes.
It was my first time to participate in such a hex tournament. There were some hex, expert player. I was a completely novice player. Yes. So I didn't know that the game of the hex. At least when I stayed in Maastricht for my PhD in 92 and 93, at that time I met first Victor Aris. It was a PhD candidate together. Yes, he almost finished, playing an end game of his PhD work. Interestingly, in his PhD thesis, last chapter, I think that's mention about the category of game solving, kind of which game solve, something like that. Then, interestingly, I've seen category of solving game. One of the most interesting to me definition was ultra weakly solved. It's like categorized. Hex game is categorized in that category. It's first player win, but without knowing the strategy. Yes. Then I had some question to my mind, to myself. What happened if we play this game hex in another board, like a chess board? Yeah. Actually, after reading this paper, I had my kind of the solution. So I really thanks to the second speaker. I would say Edouard, Bonnet, Florian, James, and Abdallah. The Abdallah will be speaker of this session. We are now pleased to hear the second speaker, Abdallah. Please.
Thank you very much. Indeed, the paper that I'm presenting today focuses on the game Slither. Slither is a recent game that has been introduced in 2010. It is a connection game, just like Hex and Havana and Twixt. And an interesting difference between Slither and Havana Hex is that it is played on a rectangular grid. So that makes a big difference, because when you play a connection game on the rectangular grid, you have to cater for the fact that sometimes when you look at 4 adjacent cells, the diagonals, you have to decide whether it's connected or not connected. It's not as clear as a hexagonal board. And so Corey Clark, when he designed this game, made some decisions. And we're going to look today at how these decisions impact the mathematical properties of the game. And so this will allow us to better understand the realm of connection games from a game design perspective, so in the direction of the mathematical properties. So what are the two main peculiarities of Slither? It is that some patterns of stones are forbidden. You're not allowed to play some pattern on the board, simply. And the second property is that stones can be moved after they have been placed. This is very different from Hex, Havana, and the other connection games where stones are not moved ever. So one last reason that we wanted to study this game was that, if you remember, a few years ago in Yokohama, I presented a paper on the complexity of Havana and Twixt. And the reduction for Havana, to prove that it was p-space hard, used the generalized geography problem that I discussed yesterday. And the reduction for Twixt used just Hex. And the reduction was much, much easier, because Hex is already a connection game, and if you can encode the board of Hex on the Twixt board, then it's clear why the second one is difficult. And for this paper, we thought, oh, maybe we can reuse Hex again as a reduction tool. And I will show you that it's possible. So what are the rules of Slither? You have a rectangular board, pairs of sides are labeled with a color, and players take turn moving an existing piece, like a king, and adding a new piece. And initially the board is empty. So in this position, assuming it is white's turn, a possible move would be to move this stone here and add a new stone there. That's a legal move. And now a possible move for black would be to move this stone there and add a new one over there, which leads to a final position with black winning, because black has a winning connecting group from the left side all the way to the right side. So those are the basic rules of Slither. And with that in mind, Corey Clark realized that that just doesn't work like that. We need something, otherwise you will end up with situations like this, where no one can win. And it's fairly easy to get into positions where you have this pattern with 2 black and 2 diagonals with 2 white on diagonals. And from then on nothing can happen, because black will never move this pawn and never move this pawn, and whatever happens elsewhere will not impact the outcome. So to avoid this, Corey Clark said these patterns are not allowed. You cannot put 2 stones on diagonal unless they are connected directly by another stone. And that avoids the deadlocks that we had on the previous slides. And so we shouldn't get any draws from those type of deadlocks. The goal of Corey Clark was to avoid draws in the game. He thought that the game would be more elegant if there wouldn't be any draw. However, when you do this, you can get into Zugzwang. You introduce Zugzwangs into the game. So Zugzwang are positions where you wish you didn't play. You wish it was the opponent's turn. And also, it creates positions where a player cannot move. So, with those forbidden patterns, although you can move stones, we can create situations where a player cannot play. So this requires adding passes to the game. So, because of that, do we get draws? Still not, and that's what we're going to prove in the paper, but I'm not going to prove it today because the proof is a bit tedious. I'll tell you the idea behind it. Alright, so 2 critical positions to illustrate this idea. First position, a Zugzwang. So in this position, if it is black to play, then white will win. If it is white's turn to play, then black will win. This is very weird for a hex player or for a Havana player, where you always want to add more stones to the board. Here it's different. So let's imagine what happens when white is to play. So if white just wants to add a stone and not move any stone. So adding a stone here is illegal because it creates a forbidden pattern with those 4. Adding a stone here is forbidden because of those 4, and this is symmetrical. So white needs to move plus add. So if white adds a stone here, then we have a forbidden pattern on the left and on the right. So even if we move something on the left, the right will remain problematic. So white cannot add a stone in the middle. Now if white adds a stone here, then we have a problematic pattern here. So this stone has to be moved here. It is not possible to move this stone here to connect them, because if we do so, we disconnect those 2. So the only legal move for white is to move a stone here and put another one there, or symmetrically to move the stone from here and put the other one here. And once white plays that move, this opens the way for black's winning move by connecting the 2 sides. The board is symmetrical, and the same thing would have applied had it been black's turn. So there are some situations where you have legal moves, but you wish you didn't. Yes?
Does black have to move also afterwards?
No, moving is optional. Placing the stone is required, but moving is optional. This is another position that illustrates that sometimes one of the pair doesn't have a legal move. So in this position, white has plenty of legal moves. For instance, white can play this pawn moving here and add a new one there. And by doing so, white would win. But if it was black's turn, adding the stone here creates a forbidden pattern there. So we would have to move something to resolve it. But moving this one is not possible because it disconnects those 2 stones. and moving this one is not possible to disconnect those two stones. So black can't play a stone here, and the other one cell is symmetrical, which means that black doesn't have a legal move, so black is forced to pass. And that raises the question, are there any positions where both players have to pass? In which case we should call it a draw. Okay. Is everything clear so far? Yeah? Okay. So I like connection games, and one very important aspect of connection games when you play them actually is ladders. And so when we studied Slither, we were wondering whether there were any concept of ladder in this game. And fortunately, one of the three authors, Florian Jamain, happens to be a very strong Slither player. He's world champion at Slither, which helped a lot in finding out all these positions that are weird. Ladders do occur in Slither, but they're a bit different from what you would see in Hex and similar games. So consider this position where white is about to win. It is black's turn, and the only possibility for black is to block here. Now white can play a stone there, and black will block. White goes on, threatening to play another stone here. Black has to block again, and now white will play a stone here and move this one. So contrary to Hex and Havana and other games where ladders can go on for a very long time, here you can stop them fairly early thanks to that moving stone possibility. Okay, so I told you that there were no draws in the game of Slither. So we know that there is no draw because the game is filled without any connecting group. That can't happen. But as to what if a player doesn't have a legal move? Well, we can show that this never happens. And how to do that? We consider a position which a player wouldn't have a legal move. So we know that this position still has some empty cells, because if there were no empty cells, then the board would be filled and there would be a connecting group. So there's at least one empty cell. So we look at that empty cell, that empty square. Is it in the corner of the board? Is it on the edge of the board? Or is it in the center of the board? So there are three distinct cases. And in each of those cases, we're going to look at what surrounding stones they could be. And then, depending on the surrounding stones, it might be legal to play on that empty square, or it might not be legal. But we show in the paper that even when it's not possible to play on that empty square because of the stones surrounding it, there must be an empty square not too far from there where one of the players can play. Which shows that as soon as there is an empty square on the board, one of the two players has a legal move not far from it. And this allows us to attempt an ultra-weak solution to Slither. So, as Victor Alice defined, an ultra-weak solution to a game is knowing the outcome without the constructive proof. So, it works really well in Hex. In Hex, we know that there is no draw, and we know that we can use the strategy stealing argument. Because there are no subsong in Hex, it's always good to have an additional piece on the board. The first player had the second player win. Then the first player would be able to use that strategy with one more stone on the board, which can't hurt them. So this shows that there is no second player win, and that there is no draw. Therefore, it must be a first player win. This reasoning doesn't work for other games like Havana and Twist, because in Havana and Twist you can have draws. There are no subswans, so we can apply the strategy stealing argument, but the best we can come up with is the theoretical result is either a first player win or a draw. And Slither is slightly different from these connection games in the sense that we can't apply the strategy stealing argument, but there are no draws. So we derive that it's a first or second player win. And I don't have any idea how we could go further in that ultra-weak solving. We can weakly solve small positions, but for ultra-weakly solving arbitrary size, I don't think it's possible with current techniques. I told you that there were node rows. That's actually when you play on a regular rectangular board. If you imagine that the edges wrap around, as has been done for a few other games like Tarot, Hidalgo, or Hex, you can get rows. So this is an example of a cylinder board. So imagine that this side and this side are the same. So you're playing on a cylinder, and black is trying to make a ring on the cylinder, and white is trying to make a column from top to bottom. In this case, it is possible to get a draw. So this is an example of a drawn position because no player has a legal move. For black, it is not legal to play here because there are two forbidden patterns. Not legal to play here for the same reason. And it's not legal to play here because there's a forbidden pattern here and another one with those two cells and those two cells. So even if black plays here and say moves this pawn here, we still have that black cell and that black cell connected in diagonal, but not orthogonally. So it's not legal for black to play, and for symmetrical reasons, it's not legal for white. And the same can happen if you play on a torus. Finally, P-space completeness of the game. Proving that Slither is a P-space complete game involves showing that it belongs to the P-space class and showing that it is P-space hard. To show that it has P-space as an upper bound, so that it belongs to the P-space class, is very easy. It's exactly the same technique as is used for other games like Hex or Twig or Atarigo or Breadthrough. The point is to say we're making progress after every move, and a polynomial amount of progress is needed to end the game. So in Hex, after each move, there is one fewer empty cell on the board. So if you're playing on an n by n board, after at most n square moves, the game will be over. So the depth of the game is bounded by n squared. The same happens in Twixt. The same happens in Atarigo because there are no captures until the very last move. And the same happens to Slither. For Breakthrough, it's not the board that's being filled, but it's how much your pieces are advanced. After each pawn move, if you define the total distance remaining to be covered as the sum of the distance from your pawn to the opponent side, then this number decreases after every move in Breakthrough, which shows that the game ends in something like height of the board times number of pieces moves. And so that's fine. That shows that Slither is a P-space problem. How can we show that it is P-space difficult? We're going to reduce from Hex. So we're going to show how one can place Hex on a Slither board. To do that, we have three gadgets. You remember yesterday I showed you that we could reduce a graph problem to Atarigo by representing vertices and edges. Today we're representing empty cells, black cells, and white cells as Slither positions. So this is the empty cell, this is the black cell, this is the white cell. And you can see that we can go from the empty cell to the black cell in one black move. And this black move is to take this stone, move it here, and add a new one there. This is a legal black move. And after black has played this move, then there's nothing one can do to contest dominancy of this cell. I can come back to it later. And something symmetrical happens for white white can move this stone there and add a new one here. And then, once we create those type of cells, we can arrange them on the board to create a hex-like pattern. So that could be a 3x3 hex board or the Slither board. So you recognize inside each of the hexes this empty cell with the two square boxes. So this is an empty hex board. Now, it's not just sufficient to say, oh, we can represent cells. The meaning of these cells needs to be preserved. So the fact that two cells are adjacent in hex needs to be reflected in Slither somewhat. So we can confirm that, let's take this cell, for example, and look at what happens after black plays in it. So black would move this pawn here and add a new pawn there. When this happens, the top group is connected to the left group. We already had the bottom cell and the right cell are connected. This one is connected via this group and this one via this group. So after this black move, those four cells are connected on the one hand and those two cells are connected on the second hand. So that's a start. What's important is that white cannot prevent the four cells on the top from connecting to the two cells on the bottom. So after black has played all the winning hex moves, black can fill the remaining cells to make the connections concrete. So here, at the very end of the game, black will come back to that cell and add a new stone here in C to connect the 4 to the 2. And white cannot prevent that. Because if white plays a white stone here, it's illegal because of the pattern. If white plays, and white can't move this one, and if white moves this, then it doesn't solve the problem of connecting the top and the bottom. So the reduction goes like this. We represent the board, and then if black has a winning strategy in hex, they can play it in Slither, and white cannot prevent that. Because black will be occupying cells one after another according to the perfect strategy, and if white plays again here, white is just wasting a move, which is never a problem in hex for the opponent. So this concludes my talk. Comparing Slither to other connection games, I have included M and K in a row because it's considered a connection game by some people. We can see that it is row-free, just like hex. However, it has Zugzwangs. I say that it can't be played with pen and pencil and paper because we are moving stones. If we were to capture stones, it would be the same thing. We would need additionally an eraser. But other connection games tend to fall into that category where just paper and pen are sufficient. When there is no legal moves, instead you have to pass. In those other games, this situation doesn't occur. And complexity is the same as for the other games, it's this phase complete. For future work, if we want to pursue in that direction, another candidate game would be Bonnet, which is also played on a rectangular board, but uses capture to deal with the problematic aspect of rectangular boards. And in Bonnet, when you don't have any legal move, you lose, which is why there are no draws in Connect. It's a direct sequence. And they can be Zugzwangs, and they can't be played on pencil and paper because of the captures. The complexity of Connect is not known yet, so that would be a possible research question if someone was interested in complexity theory. Thank you very much.
We can take some discussion time. Question, please. Okay.
Do you know anything about the three-dimensional versions of all of these games?
I do not. I read the rules of some of them at some point or considered them, but never from a serious mathematical perspective. I never really. I would assume that hardest results are preserved, but I'm not sure. And the way to show that would be to fill the board with just to fill the three-dimensional board on the top and the bottom, and you leave one layer in the middle, so that the same gadget can be applied just in the middle layer. But some effort is needed to prove that it actually works. The fact that it belongs to PSPACE would remain, because the same argument holds that you're filling one spot at a time.
Yeah, I think there is a 3D version of GoNet called Margot, where marbles stack.
Okay, Margot.
Margot, yeah.
Thank you.
3D.
Okay.
In your paper, you can improve no draws for the game, but the proof seems very complicated.
Yes. Yes. So
do you think is there any simpler way to prove it?
So
because it's hard to when
read.
I read it, it's hard to verify, convince myself that it's so,
yeah, I understand. When we were facing that result and looking for a proof, we came up with a first proof, which was a bit longer and even harder to read than this one. And when you're faced with such a difficult proof, there are two ways you can go about it. Oh, the result is not important. That's one direction. It's not very satisfying. And the other direction is to say, okay, I'm going to make it as rigorous as possible. And even if it's not easy to see the overall pattern, we can check all the individual steps. And that's what we have tried to do in this proof. We have made it very methodical. So we say, let's look at this figure. There are three possible cases. And we write down a figure for each of the three possible cases. And then we argue that in each of these possible cases, there are other possible cases. And the proof goes like a tree. And we can look at all the individual steps and check that they make sense. And that's as clear as we could get in the current version. I'm afraid that when your proof is really a huge case analysis, there's no way around something that's tedious to verify. Maybe someone can come up with a smarter proof that had a totally different technique, but maybe with this technique, that's the best we can do.
Yeah, I think for me this is rather echoing the four-colour theorem, the history of the proof of that. So it was a long proof in the journals, and then they iterated it a bit, and eventually Microsoft researcher Cambridge applied COQ to formally prove that it was correct.
Yeah, absolutely.
So then the only issue about whether the proof is incorrect is about whether COQ is incorrect, and that's been used elsewhere. So I think maybe there's a route back to formalise.
Software formalization of the proof is a very strong guarantee that even if your proof is boring and hard to read, if the computer trusts it, and if you trust this very verified piece of software, then you can trust it.
Yeah.
And that would be indeed the next step, because if we wanted to get into any more detail than we have, it would be just impossible to read for a human, so we might just as well try to implement it in code. Right.
Any other discussion points? Continue the discussion.
Thank you.